Everybody, and today we are continuing the series of the Enjoy Great Books. Our book here is New Guide to Science by Isaac Asimov, and we are now in the second chapter, Size of the Universe, and the subheading today is the farther stars. There have been more subheadings which are there in the earlier videos. So let's start. The farther stars. The stars might, of course, still exist as tiny objects set into the solid vault of the sky that formed the boundary of the universe just outside the extreme limits of solar system. It could be like that. Until about 1700, just recently, this remained a rather respectable view. It's a vault. Just outside the solar system are the stars. This was a respectable view. Until about 1700, this remained a rather respectable view, although there were some scholars who did not agree. There will always be. As early as 1440, a German scholar, Nicholas of Ch2, maintained that space was infinite and that the stars were suns stretching outward in all directions without limit, each with a retinue, of inhabited planets. That the directions that the stars did not look like suns but appeared as tiny specks of light he attributed to their great distance. It's common sense. Unfortunately, Nicholas had no evidence for these views but advanced them merely as an opinion. The opinion seemed a wild one and he was ignored. By 1718, however, the English astronomer Edmund Halley, who was working hard to make accurate telescopic determinations of the positions of various stars in the sky, what do you see in the night sky, found that three of the brightest stars, Sirius, Sirius, Procyon, Procyon, I'm not sure of the pronunciation, and Arcturus, Arcturus, were not in the positions recorded by the Greek astronomers. The change was too great to be an error, even allowing for the fact that the Greeks were forced to make naked eye observations. Haley concluded that the stars are not fixed to the firmament after all, but that they move independently, like bees in a swarm. The movement is very slow and so unnoticeable until the telescope was available that they seemed fixed. After the telescope, they realized, but till then, seemed fixed. The reason this proper motion is so small is that the stars are so distant. As you can see, from if you go to the top of hill, you can see the cars, they go very slow. It's a wonder. Try that. Or even from far when you see something, it goes slow. When you go in the train, the nearby things are going fast, but the far away things are going slow. The reason this motion is so small is that the stars are so distant from us. Sirius, Procyon, and Arcturus, Arcturus, are among the nearest stars, and their proper motion eventually became detectable. This is the turning point. So we broke the vault. We broke the vault and we realized, oh, the whole stars are infinite. Their relative proximity to us makes them seem so bright. Dimmer stars are in general farther away, and their proper motion remains undetectable even over the time that elapsed between the Greeks and ourselves. It's so undetectable, so far. So, one thing they could understand was that they're very far. The proper motion itself, while testifying to the distance of the stars, did not actually give us the distance. Of course, the nearest stars should show a parallax when compared with the most distant stars. However, no such parallax could be detected. Parallax is difficult to detect. Even when astronomers used as their baseline the full diameter of the Earth's orbit around the sun, million miles, looking at the stars from the opposite ends of the orbit at half-year intervals, they still could observe no parallax. Hence, even the nearest stars must be extremely distant. As better and better telescopes failed to show a stellar parallax, the estimated distance of the stars had to be increased more and more and more. That they were visible at all at the vast distance to which they had to be pushed made it plain that there must be tremendous balls. Even the size must be very big. Otherwise, how can we see? Of flame like our own sun. Nicholas of Cusa was right. But telescopes and other instruments continued to improve. In the 1830s, the German astronomer Friedrich Wilhelm Bessel made use of a newly invented device called the heliometer, sun measure, because it was originally intended to measure the diameter of the sun with great precision. It could be used equally well to measure other distances in the heavens, and Bessel used it to measure the distance between two stars. By noticing the change in this distance from month to month, he finally succeeded in measuring the parallax of a star. He chose a small star in the constellation Cygnus called 61 Cygni. His reason for choosing it was that it showed an unusually large proper motion from year to year against the background of the other stars and thus must be nearer than the others. This steady, proper motion should not be confused with the back and forth shift against the background that indicates parallax, of course. Bessel pinpointed the successive positions of 61 Cygni against the fixed neighboring stars, presumably much more distant, and continued his observations for more than a year. Then in 1838, recently, he repeated the 61 he reported that 61 Cygni had a parallax of 0.31 second of arc, the width of a 25-cent piece as seen from a distance of 10 miles. The parallax observed with the diameter of the Earth's orbit as the baseline meant that 61 Cygni was about 64 trillion miles away. Oh my God. 9,000 times the width of our solar system. 9,000 times the width of the solar system. What a breakthrough and the turning point. 1830. This is 1838. Because distances in trillions of miles are inconvenient to handle, astronomers shrink them by giving them in terms of speed of light. 186,282 miles per second. In a year, light travels nearly 6 trillion miles. That distance is therefore called a light year. Light year is a distance traveled by light in 1 year. 300,000 kilometers per second, or 186,282 miles per second. In terms of the unit, 61 Cygni is about 11 light years away, which means light will take 11 years. 11 years to reach Cygni. You do understand what the meaning of 11 years for light to reach? Light travels 300 kilometers in 1 second. Is it sinking in? 300 kilometers, 3 lakh kilometers in 1 second. From here till let's say, whole, my nearby city is 45 kilometers. This is 300,000 kilometers. It travels in 1 second. 11 years it will take for light to reach Cygni. Ooh. 2 months after Bessel's success, so narrow a margin by which to lose the honor of being the first, the British astronomer Thomas Henderson reported the distance of the star Alpha Centauri. This star, located low in the southern skies and not visible north of the latitude of Tarapa, Florida, is the third brightest in the heavens. It turned out that Alpha Centauri has a parallax of 0.5 second of arc, more than twice that of 61 Cygni. Alpha Centauri is therefore correspondingly closer. In fact, it is only 4.3 light years from the solar system and is our nearest stellar neighbor. Our nearest star is 4.3 light years away. Light travels 300,000 kilometers per second. And you can imagine minute, hour, 24 hours, 1 month, 1 year. Light travels that much distance and it takes 4 years for light to reach the nearest star, not the farthest. You can imagine. Already my brain is staggering. It is only 4.3 light years from the solar system and is our nearest stellar neighbor. Actually, it is not a single star, but a cluster of three. In 1840, the German born Russian astronomer Friedrich Wilhelm von Strove, announced the parallax of Vega. Announced the parallax of Vega, the fourth brightest star in the sky. He was a little off in his determination as it turned out, but understandably because Vega's parallax is very small and it is much farther away, 27 light years away. By 1900, the distances of about 70 stars had been determined by the parallax method, and by the 1980s, many thousands. 1980s, absolutely recently, many thousands, 100 light years. 100 light years is about the limit of the distance that can be measured with any accuracy, even with the best instruments. And beyond are countless stars at much greater distances. 100 light years away, they could find out the distances with parallax method and with best instruments. How interesting all this is. What wonder. That's why they say knowledge is beauty, knowledge is power. Now I'm getting that feeling. Suddenly I'm getting that feeling. I'm looking at the stars and I'm feeling the stars. Really? That is what scientists are. No, they enjoy. With the naked eye, we can see about 6,000 stars in the night. The invention of the telescope at once made plain that these were only a fragment of the universe. When Galileo raised his telescope to the heavens in 1609, he not only found new stars previously invisible, but on turning to the Milky Way, received an even more profound shock. To the naked eye, the Milky Way is merely a luminous band of foggy light. You can't even separate. Galileo's telescope broke down these foggy light into myriads of stars, as numerous as the grains of talcum powder. The first man to try to make sense out of this was the German-born English astronomer William Herschel. In 1785, Herschel suggested that the stars of the heavens were arranged in a lens shape. If we look towards the Milky Way, we see a vast number of stars, but when we look out at the sky at right angles to this wheel, we see relatively few stars. Herschel deduced that the heavenly bodies formed a flattened system with the long axis in the direction of the Milky Way. We now know that within limits, this picture is correct, and we call our star system the galaxy. So, the galaxy was discovered. This is a third turning point, which is actually another term for Milky Way because galaxy comes from the Greek word for milk. Herschel tried to estimate the size of the galaxy. He assumed that all the stars had about the same intrinsic brightness so that one could tell the relative distance of star by its brightness. By a well-known law, brightness decreases as the square of the distance. Interesting, no? So if a star is 1/9 the brightness of the star B, it should be 3 times as far as that of B. Square the distance. By counting examples of stars in various spots of the Milky Way, by counting samples of stars in various spots of the Milky Way, Herschel estimated there were about 100 million stars in the galaxy altogether. 10 crores. From the levels of their brightness, he decided that the diameter of the galaxy was 850 times the distance to the bright star Sirius, and that the galaxy's thickness was 155 times that distance. We now know that the distance to Sirius is 8.8 light years. So Herschel's estimate was equivalent to a galaxy about 7,500 light years in diameter. 7,500 light years in diameter is Milky Way. It's not some small thing. 7,500 light years. It takes 7,500 years for light which travels at, again, I repeat, 300,000 kilometers per second to traverse that. Wow. And 1,300 light years thick calls. This estimate turned out to be far too conservative. This is also conservative. But like Aristarchus, over conservative measures of the distance to the sun, it was a step in the right direction. It was easy to believe that the stars in the galaxy move about, as I said before, like bees in a swarm, and Herschel showed that the sun itself also moves in this manner. Sun also moves. By 1805, after he had spent 20 years determining the proper motions of as many stars as possible, he found that in one part of the sky, the stars generally seemed to be moving outward from a particular center, the apex. In a place in the sky directly opposite to the first, the stars generally seem to be moving inward towards a particular center, the anti apex. The easiest way of explaining this phenomenon was to suppose that the sun was moving away from the anti apex and towards the apex, and that the clustered stars seemed to be moving apart as the sun approached and to be closing in behind. This is a common effect of perspective. We would see it if we were walking through a grove of trees and would be accustomed to the effect that we would scarcely notice it. The sun is not, therefore, the immovable center of the universe, as Copernicus had thought, but moves, yet not in the way the Greeks had thought. It does not move about the earth, but carries the earth and all the planets along with it as it moves through the galaxy. It moves through the whole galaxy. Modern measurements show that the sun is moving relative to the nearer stars towards a point in the constellation of Lyra at a speed of 12 miles a second. Beginning in 1906, the Dutch astronomer Jacobus Cornelis Kapteyn, Kapteyn, conducted another survey of the Milky Way. As he had photography at his disposal, and knew the true distance of the nearest stars, he was able to make a better estimate than Herschel had. Captain decided that the dimensions of the galaxy were 23,000 light years to 6,000 light years. Thus, Captain's model of the galaxy was 4 times as wide and 5 times as thick. Oh my God. As Herschel's, but it was still over conservative. To sum up, by 1900, the situation with respect to stellar distances was the same as that with respect to planetary distances in 1700. Interesting, no? By 1700, they were clear about planetary distances. By 1900, they were clear about stellar distances, nearby stars, Milky Way. To sum up, the 1800 situation with respect to stellar distances was the same as that with respect to planetary distances in 1700. In 1700, the moon's distance was known, but the distance of the farther planets could only be guessed. In 1900, the distance of nearest stars were known, but that of the more distant stars could only be guessed. So slowly we're going outward. Amazing, no? This whole this whole part is the size of the universe. This whole chapter, and the heading of the chapter is the universe. So, first chapter is the universe. We'll know everything about the universe, really. Black holes and neutron stars and everything. Everything conceptually, logically, and in terms of observation, and in terms of how we arrived at it. I mean, what more do you want? What more does a student want? He'll know everything. And that he covered physics, chemistry, biology, technology, brain, geography, all sciences like that except maths. And maths also I give a little bit at the end. All this is the thing we read. And we combine that with a wonderful understanding of history, connect it how everything, and we connect it to literature and arts. That's when we go complete what is called integrative education, and that is when you get the full feel of this universe where we live for a short while. And I think even death you will be able to accept then and only then. Yeah.